Hey there, lovers of mathematics. This lesson today is rational functions, find every asymptote ever. So in a previous video, I think we talked a little bit about how to find horizontal and vertical asymptotes. I'm going to kind of go over it again here real quick just because it's really important, and then I really want this video to be just, if you want to know how to find an asymptote, you can go to this video and it'll be that kind of a resource for you, I hope. So let's first start with vertical asymptotes. Vertical asymptotes occur whenever we divide by 0. In other words, whenever the bottom, the denominator, is 0. So when is this 0? Well, I'm going to claim that it's whenever 2x squared minus 1 equals 0. And if I were to solve this thing for x, I think that I would get down to like maybe x squared equals 1/2. Add the 1 divided by 2. And then if I take the square root of both sides, I'm taking the square root of a variable, plus or minus the square root on both sides. So I think I get down to x equals plus or minus the square root of 1/2. And check me on this, but I think that's the same as plus or minus 1 over the square root of 2. And I think that that's the same as plus or minus the square root of 2 over 2. So some good kind of rationalization review there. But I've got asymptotes at square root of 2 over 2, positive and negative. So that's where my vertical asymptotes are. Horizontal asymptotes are a little bit trickier. So let me clear my screen here of the horizontal stuff, vertical stuff. Now the horizontal stuff is a little bit different. So let me give you the rules for horizontal. If the degree of the numerator, okay, so you're going to write that down, I'm going to abbreviate. Numerator is less than the degree of the denominator, then my asymptote is at y equals 0. Okay, so if my degree of the numerator is less than the denominator, I've got an asymptote at y equals 0. Stop, that's it. Okay, so if I had an x, my degree on top was maybe a linear function, something like x plus 2, and the bottom was a quadratic function, or to the power of 2 second degree, like maybe 2x squared minus 1, then my asymptote would be at y equals 0, which remember is just the x-axis. All right, so let me clear that. Now, what happens if the degree of numerator and denominator, degree of numerator equals the denominator? What if that happens? Well, then I'm looking at the ratio of the coefficients, or the leading coefficients. So this would be then asymptote is the ratio of leading coefficients. All right, so in my example here, the degree on the top in the numerator is 2, right? That's a degree 2. I've got that little squared up there. And the degree on the bottom is 2 also. So if I want to know what my asymptote is, my horizontal asymptote, that's going to be at 3 over 2, or y equals. So in this one I would have horizontal at y equals 3 over 2, right? Because I've got a 3 divided by 2, so my horizontal asymptote is at 3 over 2. I'm looking at the coefficients, looking at the leading coefficients, the ratios of those two numbers. All right? Now, you're probably thinking to yourself, well, what happens if the degree of the numerator is greater than the denominator? Well, that's a situation where we might have a slant asymptote, which is mostly what I'll talk about in this video. It's also possible to have a parabolic asymptote, which we won't really get into, at least in my pre-calc class. So I'm just going to kind of show you the slant asymptotes, but it's certainly possible that you'd end up with a parabolic asymptote also. All right, so let me clear that screen, and we'll move to the next thing here, slant asymptotes. All right, well, the first thing I'm going to do is rewrite this at least a little bit nicer. So this is actually x squared minus x minus 2 divided by x minus 5. All right, and my process for finding a slant asymptote is to divide the denominator into the numerator and see what my remainder. Oh, I'm sorry. Divide the numerator by the denominator and see what I end up with. So since my bottom here is x minus 5, my denominator is x minus 5, I'm going to use synthetic division, and I'm going to take 5, and I'm going to divide x minus 5 into x squared minus 1. So this would be 1, negative 1, and negative 2. All right, bring down the 1. 5 times 1 is 5. Negative 1 plus 5 is 4. 5 times 4 is 20. So this is 20. Negative 2 plus 20 is 18. So this means that my function, my resultant function after I divide, is x plus 4, remainder of 18. If I'm looking for asymptotes, I do not care about the remainder. My asymptote is whatever function I end up with. So x plus 4 is my asymptote. Asymptote. Okay. Now it's possible, like I said before, that you would end up with a parabola down there. I won't spend a lot of time in class on that, but it's certainly possible that you do division and you end up with something that is x squared, which should be a parabolic asymptote. This is the way to find them. So let's take a look at what that looks like on the graph. So I'm going to clear the screen out here and go to the next slide. And so this is the graph of the function here in pink. That's my function. And then the asymptote, you can see, is a slant asymptote because it's not straight up or down or horizontal. It's right here in red. And probably would have been a better color, but that's the line, y equals x plus 4. And that's it. That's how you find slant asymptotes. All right, let's look at one last discontinuity here. Let's go down to holes. What happens if when will there be a hole in the graph? All right. Well, this is gonna once again. Oh my goodness, what happened? All right. Now let me rewrite this so it's a little nicer. X squared minus 4 divided by x minus 2. Well, the first thing we should do whenever we see a rational function is see if we can simplify it. And I'm going to claim that this top thing can be factored into x minus 2 times x plus 2 divided by x minus 2. Look at this. The x minus 2's cancel out. So this function is actually just x plus 2. Sweet! So that means that this thing is just a line, right? So I can graph the function x plus 2. I've been doing it since I was in 7th grade, so that's not a problem at all. And actually, I think a linear function is continuous everywhere, right? Except that I can't divide by 0. Right? So even though I end up down here at a linear function, that doesn't change the fact that my original function has a problem at x equals 2. Right? So if you, these are called removable discontinuities, so if you remove part of your function in that way, you have a hole wherever you do that. So there is a hole at x equals 2 when I'm dividing by 0. It's not a vertical asymptote, right? Because my function will look like this x plus 2. It will be a line. I'll show you a picture in a second. But there's actually a hole at x equals 2 because I divide by 0 there. So be very careful. Make sure you factored and simplified as far as you can before you go saying that at 2 there's a vertical asymptote, right? So let's take a look at the picture of the graph. And I love this graph because you look at it, and at x equals 2, so we're looking right here, right? We're looking right here at x equals 2. It doesn't look like there's a hole there. If I take away the mark, it doesn't look like there's a hole. And your graphing calculator isn't actually going to graph the hole. But you and I were smarter than the graphing calculator. That's why I'm not really sure that's why anything, but we're smarter than the graphing calculator, and we know that there's actually a hole here. So your graphing calculator maybe won't even graph the hole. So be very, very careful. You've actually got to look at these functions analytically and see where, algebraically, I'm sorry, and see if there's a hole or what actually happens when we simplify the function. And that's it. That should be pretty much every asymptote, and then that hole is a discontinuity. So anything you should be able to handle after watching this video. I hope